I'm going to discuss today with you how the Axivion suite and the Axivion architecture check can be used to recover software architectures. So instead of if you're not in the ideal world where you already have a software architecture, you have it documented, you're pretty sure that the software actually follows the architecture. Let's start from a perhaps more realistic world where you have to recover what your software architecture actually is. You have an idea about it. You might know how the software works, but you're not that sure about it. So let's see how we can recover the software architecture, how we can use the architecture checks in Axivion to verify if your idea is correct and to get step by step from an initial idea of how an architecture could look like to the actual architecture that is then really what goes on in the software. I'd like to start with some background to allow you to catch up so that you're not immediately thrown into architecture checking, but you have an idea about the context in which this all takes place. The architecture check is part of the Axivion suite, one of the many things that Axivion can do. Basically a static code analysis tool with the usual features like checking coding guidelines, in particular for safety critical or security critical aspects of your software, be it MISRA rules, CWE, and so on. We find that code, we find cycles in the code, both call cycles and include cycles. There's a lot of metrics. If it can be counted, we probably do count it. And we analyze clones, that is copy and paste with changes of your code. So all certain quality aspects, different aspects to quality, different aspects that might allude to places in the code that should be refactored, that should be changed to reduce what we call erosion of your. And the part I'm going to talk about today in the upper right corner, the architecture verification. And that's really about ensuring compliance between your documented architecture, what you have in some UML tool in the minds of your developers, or in some other place, be it sketches, be it a wiki, some documentation on how your software is composed, how components should interact. And you want to know, does my code actually do what I've documented here? Do the components really interact in the way that I've drawn? So we're talking about the upper right-hand corner here, the architecture verification. Let's give you an idea how that works. Simple example system where A is some user interface. You could think of your car dashboard that is supposed to display the temperature. Or maybe it's supposed to display a little snowflake once the temperature is too low. It's summer now, but I'm pretty sure you can imagine. There's a middleware going on in the B component, which is doing some calculations, converting hardware values to readable values, and doing intermediate data work. And in C, you see there's the hardware layer. That's the actual sensor that is producing temperature values in Celsius. If you prefer Fahrenheit, give me a minute, we'll get there. So what happens is, behind this specification, behind this rough sketch of how the system is supposed to interact, there's an implementation behind it. And you see that the architecture specification already has a pretty broad but pretty important idea of how this works. The UI in component A uses the middleware in component B, and that one uses the sensor. So this is pulling, right? The UI pulls the data, maybe periodically, and updates the user interface. If the architect had envisioned the system to do pushing, if the temperature changes, please update the UI, one of the errors would have been the other way around. So this already shows a pretty important design decision, even though it's a simple example. Now what happens is, in a system that is not as simple, we see that the implementation usually differs from the architecture specification. For instance, due to misdocumentation, misknowledge, maybe time pressure, a coding review that didn't spot it, somehow a mistake sneaked in, and somebody took a shortcut. Somebody for a second interface, for a second part of the interface needs the temperature again and pulls it immediately from hardware. You see, the edge from A to C is bypassing the middleware. And that's not what's supposed to happen. What's the consequences of that? What's the problem here? Well, initially, nothing. This is working, right? Maybe there's test cases, the code has been tried out, everything is fine. The architecture is violated, but that fact does not manifest in a malfunction. So we have erosion. The code is not in a good state. There's this violation of the architecture that might have consequences, but they don't show. The code works as intended. Now let's spin this a little further. And as promised, we're doing Fahrenheit now. So somebody realized that the display should probably be able to switch between Celsius and Fahrenheit. And the place to implement that is, of course, in the middleware. So if the baby car is now sold in the US, the temperature sensor is still the same. It produces Celsius values. We're converting them to Fahrenheit. Now remember the shortcut. If we map that to the real software system, that shortcut now has consequences. Namely, if you think of this greenish box being the part of the software that does the conversion from Celsius to Fahrenheit, then in the component A, we now have some part of the display being behind the component because it's correctly behind the middleware, and that shows Fahrenheit, whereas the component that took the shortcut is still displaying Celsius. Now that has to be fixed somehow. And how is that fixed? Well, somebody realizes we're off here. This is now mixing Celsius and Fahrenheit. Celsius we have for the sensor, Fahrenheit we have after the middleware. But over here, somebody now realizes there's an issue. Now it manifests, and we see that the actual output in the user interface now is a mixture of both units of measurement. This is supposed to be fixed. But now, some time has passed since the shortcut was introduced. Maybe it's not the same developers. Maybe it's a different test case, a different team. Maybe the person who did the shortcut is not the same person who realizes that there's now a misconnection. So what happens? Actually, what happens usually, and we observe this often in source code, is, well, okay, got to fix that. The Celsius I see in component A is not correct. I'm introducing a new conversion from Celsius to Fahrenheit, converting the other value as well. And you see now I got a second greenish box, which is basically copy and paste. That's a clone in the source code now. I've copy and pasted part from B to A. At least the display is consistent now. I've seen Fahrenheit everywhere. But now I got a source code clone. So you see the architecture violation, while it was not responsible for software malfunction, is now responsible for the quality of the source code declining further and further. In particular, it's eroding further. We've introduced a clone here. How do we prevent that? Our idea would be to take this architecture specification, put it into some machine-readable format. That's the same sketch, right? I just took it from sketch to machine-readable thing. And then we compare to the implementation. And that comparison shows that, okay, yes, there is an interaction from A to B. There is an interaction from B to C. But we also find interaction from A to C. And that interaction does not have a corresponding allowed interaction in the specification. And right at that time, imagine this running in a CI build, running automatically on each of your branch, running automatically in the IDE of the developer, just implementing that. It can give immediate feedback, give immediate information, and realize, okay, what I just did is taking a shortcut, bypassing the middleware, and violating the intended architecture of that software. Now I can immediately fix that before it makes the code quality decline further, even though there wasn't any immediate consequence to it. So what can I do now? I can remove it. I can do the proper implementation, remove this dependency from A to C. I can document it in the sense of, well, maybe that is the intended specification. My specification was wrong and it would just be allowed for A to interact with C. Or, last case, accepting the deviation. So that's also supported by the tooling. If you, for whatever reason, have to accept the fact that this deviates, you can do so. So these are the three possible outcomes. Either the model is now correct, or the model itself is updated, so there is no edge from A to B. Well, or we just have to accept the fact that we are violating the architecture, but we know about it, we have it documented, we can implement further remedies at some later point in time. The important part is, even if we accept temporarily that we are violating the architecture, there are no surprises anymore. Plan and implementation are in sync. All our assumptions about the software architecture are reliable. There are no workarounds necessary. We don't cause additional erosion. And we are immediately, in our nightly build, in our IDEs, remembered that this is a situation we are currently in. So much for the theory. Let me reshare and go to how this looks like in an actual live demo. So I've got a system here, which is the ISO8glib. It's a communication library for a CAN bus in agricultural machinery. Just so that you know what the situation is where this software would be used. And as I've said, we compute several interesting facts about this software. There's some rules being checked on it. There's metrics being counted, that code, cycles and clones, as I've said. And you also see the dashboard shows these architecture violations, and there's some 400 of them. You see a trend chart. You see that it has been analyzed periodically over time, and you see how your issues evolve. If I go for all the issues or for the trend, so that's the change in the last two revisions, you see which issues there are, what part of the internet architecture they violate, and how this all comes together. We'll get back there, but let me show you how these issues are actually produced, what you would need to do to get to the point where you can report them in such an interface and give them to your developers. So let's go to another tool, which is called Gravis. And that data you see here is what we call a resource flow graph. And it shows exactly that, how resources flow through your software. And a resource is basically anything you can imagine. Not going into the technical details, but to give you an impression, this is all generated by our tooling, by our compilers. And inside this declaration facts view that I'm now going to open, you see everything that is inside this ISO8glib. Let's maybe zoom out a little and try to make this a little less confusing. Oh, still work on it. Okay. So, it shows as nodes all the possible things that are part of your software, which is routines, objects, maybe members, there's macros, types, and everything that you can have in your software somehow. As an example, let's take the routines here. So every red box is just a routine inside this ISO8glib. You could also, for instance, go for objects, in particular maybe variables and constants, and you see, okay, these are all my variables and constants. Everything that is part of your software, our compiler put inside this declaration facts view. Now, interactions between these objects, interactions between these objects are given as edges. So let's see, given that these are routines, what can routines do? Well, they can call each other, either explicitly or implicitly. So let me put these edges back. And you see, these are calls between routines. Let me pull two out. There's a routine with a somewhat longish name, gthrow pthread condition time wait. And you see that at the very beginning of the edge, there is another routine. They are connected by this bluish arrow, meaning this routine is calling that routine. Now you can imagine that what an architecture check would need to do. It would need to figure out, okay, what's the component this routine belongs to? What's the component that routine belongs to? How do they fit with the components in my UML diagram? Is this A, B, or C? Is this middleware? Is this UI? The same on the right-hand side of the edge. And then we can, of course, compare this edge to the components where these two belong to. Tricky thing is you just don't want to do that by hand, because if I show all the possible objects with all the possible interactions in the software, you see this immediately becomes absolutely confusing. And that's a somewhat smallish library. So how to automatically and systematically, from this flat view that just shows, okay, there's a lot of interaction in your software. It's doing a lot. Things are accessing and using other things a lot. How to systematically uncover the architecture now? Because currently it's just a flat view of everything floating around freely. Well, let's start from some initial idea. And for this ISO lib, there is some initial idea given in a picture. That's something that you could have for your software as well. And I'm pretty sure you either have it as a picture, a UML diagram, or something like this is in the minds of the developers, and one would have to pull it out of there. So what does it say? Apparently there's 4 big components in this library. There's the communication, the driver extension, the hardware abstraction layer, and then some hardware and drivers, but we are going to ignore that for now. And let's do just the 3 layers on top. We see that there's interaction between the layers. And now the important part is that is not a machine-readable interpretation. This is just a picture, right? So to create an architecture check from this, we would have to figure out what the arrows actually mean. And for some reason, there's different arrows, right? The hardware abstraction layer is divided into some subcomponents, and there is individual arrows from the subcomponents to each other. But there's just one big arrow from the driver extension to the communication. That probably has some meaning. Let's see if we can recreate that later on. Also, the arrows have a direction, obviously. But is it really the case that the whole thing is driven by the BIOS and the operating system? Is the BIOS and the operating system driving the hardware, and the hardware is then accessing the drivers, and the drivers are accessing the communication layer? It's probably the other way around. The application on top of all of that is using the communications, and they are using the drivers, and they are using the hardware abstraction layer. So with the arrows, you're just never sure, is this data flow, is this access, what exactly do they mean? But we will put a meaning on all of this in the architecture diagram that the check can then consume. So you have to make it precise. You have to get to a point where you are sure how your architecture should look like. But you can do it interactively, step by step. Just starting from guesswork like I'm doing right now to a precise representation. That's not my software, it's not my picture, it's not my diagram. So I'm just doing exactly the guesswork I'm just doing. And let me show you how that would look like using the Axivion suite. So first of all, the architecture start describing the architecture. We tell the check that this is supposed to be our architecture, and it's empty. We don't know anything. But either from a picture or from speaking to my developers, I have an idea. I know there is a hardware abstraction layer, so let's put it over here. I know there will be driver extensions. And I know there will be a communication layer. Let's start with these three big components, because as I don't know the architecture yet, the scheduler looks somewhat confusing, right? It's not its own component. It doesn't have arrows. It's somehow just on top of all of these. So how does that beast work? I don't know yet. We'll find out. But I have a pretty good idea how these work. And my idea is, okay, the communication layer is allowed to use the driver extension. The driver extensions is allowed to use the hull. And I'm currently doing these edges that say source dependency. So it's kind of an anything goes. The communication may use the driver extension in any way. Calling, writing variables, reading stuff, instantiating classes, what have you. A restriction could be that you want to do interfaces, and then you would say, okay, this is only for calls, no other interaction. Part one. Now we got to tell the system which source code belongs to which of these components. Again, we add a new view. Usually called the mapping. We tell the check that this is supposed to be the mapping. And you see this now has a side-by-side view of anything that goes on in my software. It's my files, my folders, and inside the folders, it has header files, of course. Inside the header files, we have namespaces, there's routines again, there's types, and so on. And I can now individually map all of these to communications, drivers, and hull. I'm doing it manually now, just by drag and drop. But of course, in a real-world system, that would be automated. Going by a naming pattern, going by folder names, going by information about routines. Are they public? Are they private? Is this a .doc file? So anything can be taken into account, but we would want to have it automated in some way. I'm doing a little guesswork again, as I don't know that software. So let's try to uncover the architecture. The hull folder sounds like, yeah, that is probably the hardware abstraction layer. There's a util folder that isn't even in here. There's a scheduler. Okay, I wanted to talk about that later. If I look in system, there's a CAN bus. And the CAN bus seems to be split in drivers and COM. So I'm guessing driver extension is the driver here. And COM is probably the communication. I could do subnodes for these subcomponents, but let's not go there to save a little time. It would work exactly like it did right now. Okay, so we have some parts of the source code mapped to some components. We have an idea how their interaction should look like, and automatically generated from the Axivion suite, we have all these interactions. So let's overlay all of that. Let's use all of that. Put it together into what we call the architecture check. And what it does is it provides me with the picture I had a moment ago. Again, this is my architecture view. But this time we get red and green edges inside it. And you see, okay, there is some stuff going on in all directions here. This is green, so the communication is indeed using the driver extension. This is green, so the driver extension is indeed using the hardware abstraction layer. But I also see that the driver extension is using the communication layer, and the hardware abstraction layer is using the driver extension. That doesn't sound right. Now we can go explore. We could open up these boxes and see, okay, there's my communication layer. And we could further go into the software and see, okay, what part of the driver is then causing this edge. And you can interactively explore all of this. There's the ICANN customer CH, which has the ISO glib namespace. Inside, there's this CAN customer C, and that class apparently accesses the network management and the proprietary messages part of the communications layer. That might be now, as I've said on the slides, that might be a violation. It might be a misqualification. It might just be that this part of the software doesn't belong to the drivers. Maybe it belongs up here to the communication layer. So maybe I misqualified something. The important part is I can do a double click as well, and you see, okay, this is all the violations. This is taking parameters of certain types, namely receive stream identifiers as the target. So these types are being used. I can't tell you if that is correct or not, but we can generate the picture that would help both the architects and the developers to uncover what they need to talk about. To make this a little simpler, maybe go for one of the edges, hide that one. I gotta zoom a little here, but if you have a bigger monitor, maybe big screen in some conference room, this is exactly the picture that architects and developers could now talk about, could use to find out what's the intended action here. The communication layer is using the driver extension. That was my interpretation of that arrow. Apparently, there's also the reverse going on, and you can interactively move through the software, find the interactions right down to the very innermost source code, and see, okay, it's two classes. It's ICANN customer C and the proprietary message handler C. These two classes interact, and that's in the opposite direction. And you could even go down to source code. If you click on these edges, you could open the source code for that edge. Go to the source code, see what caused it, see when it has changed, and then get to a state where now you know your software does not follow what you designed it to follow, and you have all the information you need to talk about that fact and to find out whether you want to change the architecture. Maybe the edge is missing here, maybe the source code is right, or whether you want to adapt the source code to get rid of these usages. Now maybe let's do a last try here. Just assume that was correct. Close a few things here. So let's say, okay, that discussion found out that indeed these three can use each other. It's just the communication that should not access the hull. So usage in all directions, but no direct usage. Again, working hypothesis. Or that could be the result of what the architects and the developers decided is correct. So adapting the hypothesis here. Well, it is fine to go in the opposite direction, but it's still not fine to directly go from communication to hardware. Again, not leave the middleware out of the picture when implemented. And after the architecture has been updated, we can ask the system, well, rerun the analysis. Do it again. Again, compare all the interactions in your software to what you have given as a target architecture here. And we see, okay, obviously there's more green now. I just added these two interactions to the source code, to the model. They're still in the source code, so now it's green. And there's just one case of the communication layer bypassing the hardware abstraction layer now. And if I look at that, it's a lot of type usages and parameters of types. It is all just one type, EQ time T and get time. So it seems like there is no driver extension to do times, to do current time or time taking. And that is done via communication and hardware abstraction layer. So what I found is that's a prime target for refactoring now. There's either the driver extension needs to have some way to do time, or it should be allowed, time should be a separate entity in this whole architecture diagram. Again, that's then for the architects and developers to decide. As a last step, we've kind of worked our way around that scheduler, because I don't know how this is supposed to work. It's not in this it's not in the arrow and boxes structure of the picture, so to speak. So let's just try again. You can use this absolutely exploratively. I'm putting the scheduler just in the system. I know that it's there, but I have no idea how it's interacting. So let's just pretend it's not. Let's ask the system to tell me how it's interacting. And what I'm doing is I need to update the mapping, of course. I need to tell the system what the scheduler, what part of the source code makes the scheduler. I'm luckily guessing probably the things in the scheduler folder. So map it over here. But again, I have no interaction plan. I have no idea how that system works. I've just put it there. But if I put this as an input in the architecture check, it will tell me how it behaves. I'm now seeing how the scheduler interacts. Apparently, the scheduler is accessing driver extension and hull. That's these red arrows. Why are they red? Because I have not given the scheduler any permission to use anything. So this is a violation. Also, the scheduler and the communications are using each other. So given that this is somehow just on this picture, it behaves differently. It accesses and communicates in both directions with the communication layer, which I see, okay, but not with the driver extension. And again, the scheduler seems to access the hardware abstraction layer. Why is that? Let's have a look. It's our friend. It's the time taking again. So let's disregard that one. That is time taking. We have already learned that is supposed to be refactored, and we assume by looking at this picture that the scheduler is supposed to use drivers and communication, would somehow add up with what we see here. Again, discussion between architects and software developers to find out if that's a valid assumption. And if we do so, we can now connect the scheduler to the communications and the driver extension, rerun the analysis, and understand, okay, this just gives me a somewhat clearer picture. This is the time taking, this is the time taking. Oh, what's that one? Why is the communication layer actively accessing the scheduler? And again, you're just a double click away from understanding the interactions here, seeing which routines are called. So the communication layer is accessing constructors and destructors of scheduler tasks and is timing events. So that's probably intended usage. We could now separately allow that, giving an edge that says, okay, calls are fine, maybe not. Again, that's for your architects and developers to decide. But you give them all the information to discuss that, to show source code positions, to show the interactions, to explore inside these systems, explore inside the components, how they are created, how they are composed, and which of these interact in which ways. Again, as this is getting somewhat complicated, maybe focus on some aspect. Hide everything, just go for calls. You can get a clearer picture. Maybe just go for inheritance, whatever is like the first interesting property in your system. If you just go for calls, you already see, okay, here are the calls from the scheduler, from the communication into the scheduler. Are these extended? Are they expected? Are they accepted? Is this how the system should be designed? And if you have just a rough idea, back to the architecture, draw some edges, draw some components, get some interactions, and you can interactively find out if this is now our architecture, if this is what we think how it looks like, would that give us green arrows? Would this be what the software actually does? So one thing is, you of course want to design a clear and correct architecture, but you can also step by step make your way to what you currently have. And then from there on, work towards the system that you actually desire to have. Work from the architecture you have right now, from the state of your system, towards the ideal system. How? Well, get the edges right, understand how the system looks like right now, and then delete the one that you don't want. It will immediately show up with your developers. It will immediately show up in the IDEs and in the web interface. So as promised, once you've done these steps, the analysis can be persisted. It can be rerun for branches, for nightly builds, for main branches, inside IDEs, and wherever you need the results. How do they look like? Basically, if I go for one of these, you see, okay, between these two executions of the analysis, this code change, just that one code change that happened here, introduced 2 additional violations. There's 2 architecture checks going on in our test system here. These are new. They have an owner. It's assigned to some software developer. The developer has been notified and can now go look at the details of that and see what exactly is happening. And how this is presented is you get 2 source code views, one being the pausing point of the edge, so that's the left-hand side, that's the right-hand side, and you see a quick view that says, okay, how was this supposed to look like in my architecture design? How is it actually looking? And you see, well, it's the task controller accessing the common system access here, meaning communication to hull. So that's exactly the representation of one of the red edges that we just saw interactively. It's tracked over time. It's presented inside IDEs. It's presented inside your pull request. The information is right where you need it. And from there on, you can go exploring further, improve, maybe add the subcomponents for driver extension and communication, and successively move the current picture of the architecture from the heads of your developers and from your documentation to machine-readable, precise, and well-described description, and then to a well-described and precise description that actually describes what's really happening in your software. That's it for my demo. Gave you a rough idea of how the architecture check worked, how the results are represented, and what needs to be done to go from system to architecture check. Most of it was generated by our tooling, the mapping and the architecture I just designed, or we can import from external tools. We can do parts of it automatically. Again, all depends on your project.